Good afternoon, students. I hope you're doing fine.
Good afternoon, ma'am.
Good afternoon.
Good afternoon, ma'am.
Good afternoon. Good afternoon. Good afternoon, everyone. We are going to discuss the execution of register reference instructions today. In the practical class, we are going to discuss the execution of register reference instructions today. In the practical class, we had seen how to make the basic machine. And when I say how to make the basic machine, what I mean is what all registers need to be there, right? So we made the registers and we made the fetch sequence now, right? And we also made our main memory, right? The next step is to start the execution of the instructions. So as I told you, the register reference instructions are the easiest to execute, right? So I'll be first doing the register reference instructions with you. I have done only CLA with you. I'll be covering more register reference instructions today. That will be the topic of discussion for today. And in the next practical class then, I'll revise what we had done in the last class and take you forward for showing you how to execute the remaining register reference instructions. Okay, right? Clear?
Okay, ma'am.
Yes,
Begin?
ma'am. Yes,
We
ma'am.
begin?
Ma'am.
Yes, ma'am.
Thank
Yes,
you.
ma'am.
Do let me know when my screen is visible to you. Okay.
Ma'am,
Yes.
ma'am, are you in college?
Yes.
Ma'am, please show us our classroom.
Okay. I'm not in a position to show you your classroom. The lab right now, taking the class from the lab. So this is you can possibly only see the blackboard right now. Okay, because I have a laptop and I'm not taking your class because I have to share many things, right? So I can't take your class on a phone. Otherwise, I could have, just given you a glimpse of your college.
Ma'am, please show the classroom now.
अभी नहीं बेटा. So I think now everything is
Ma'am, you
opening.
can
We
join
are back in the
again.
college almost, and maybe you will also join soon. Right? Okay. So I'm just going to be presenting my screen to you. Let me know when this is visible. So the agenda for today, as I told you, is to see the execution of the register reference instructions. Okay, so I had already explained to you when are the register reference instructions. That means any of the register reference instructions executed when D7 is equal to 1 and I is equal to 0. Okay, I had also told you that normally up till this time we had been looking at the I mode, that is the indirect mode bit, as the 15th bit. But now onwards, there is a little change. That does not make any difference, by the way. Okay, so what are we now doing? We are treating the last three bits, that is the 13th, 14th, 15th bit, to be going to the decoder, and this 12th bit as the indirect bit. Okay, so this is the only change. As a result, you will find that for any of these register reference instructions, we first need to have this prerequisite true. Okay, what is this prerequisite? Prerequisite is that D7 must be 1, and then after that, so the 12th bit, right? I should be 0, and then as you could see here in the flowchart we had discussed, the register reference instruction is executed in the time signal T3, right? So these three prerequisites are to be satisfied, first of all, for the execution of any of these register reference instructions, and commonly they are denoted by a single letter R here. Okay, so you can see R here, right? So R prefixed here before the micro instruction which is listed for the execution of these register reference instructions. Now, what is this B11? Let us look at this example that I've put here. Although I think I explained this to you last class, but for the sake of continuity and revision, let me do this again. So please see that D7 means 111, right? I dash means 7. When I convert them to hex, right, they start denoting E. Okay, is that okay? Right?
Yes.
Now, if you remember, we had decided in this instruction format that you see here that these 12 bits will signify the address of the operand in case this is a memory reference instruction, right? But if you remember, I told you that reference instruction or a IO instruction, in the sense that since for register reference and IO instructions, I do not have to fetch any operand from the memory, we don't need these bits to specify any memory address, right? So I can put them to another use. Okay, and that is why when we saw this division of the opcodes, if you remember, if I generally follow this division, someone could have thought that how many operations are supported here? Only 1, 2, 3, 4, 5, 6, 7 memory reference instructions, right? So memory reference opcodes, only 7 memory reference operations, and 2 other operations, 1 IO and 1 register reference, right? But it is not so. But it is not so. In fact, we have very intelligently put the remaining bits to use in the register reference and IO instructions to indicate the various operations that need to be done. So for example, when this 12th bit, what will be the number of this 12th bit? It will be B11 because we start the counting from 0, right? So this is B0, B1 up till B11. So when this B11 is 1, initially when all of these are 0, then no register reference operation is implied. When this is 1, then CLA will be performed. Then CLA is implied. Okay. Then when the B10 bit is 1, then clear extended bit, which is the next operation, will be implied. So how do I specify clear E? I simply put all the bits to 0 except for B10. So this B10 could be turned to 1. So you can see this here. So for CLE, this will become okay, right? So what does this become? Now, Please see. I'm sorry. So please see. This is E800 in hex, right? Is that clear to everybody? For CLA, the equivalent code of this instruction in hexadecimal would be E800. Is that right?
Yes, ma'am.
ma'am.
Yes, ma'am.
And for CLE, it should be E4. What is this? 4, right?
E400.
Ma'am.
E400. So it will be E400 and so on, so forth. And then for the next instruction, because B9 is involved, so it will be so what is this? This will be
E200.
E2, right? So this is how the opcodes are made. Okay. So is this clear? So this is how these opcodes will be formed. Okay. Now let us look at the instructions themselves. Okay. So clear A means clear AC. So that means, as we had also seen the implementation of this in CPU sim last time, the remaining implementations also now you will have to do in the CPU sim. So please understand these very carefully here, because in the next lab session, in the first lab session of this week, you are required to, each batch is required to complete on its respective day what we had done on the in the last interactive lab session. That means implement the fetch routine and CLA. Okay. So for instance, B1 had a lab yesterday, B2 has today, right? And B3 has on Friday, right? So you have to do what? You have to complete fetch routine and CLA. Okay. Now in
Excuse me,
the,
ma'am.
yes,
Ma'am, but where we have to assign our
that
lab
I will
work?
tell you. That I will tell you. Okay.
Okay.
First, you have to do it on your machines. Okay.
Ma'am,
And I will also show you. I will show you. I will show you
ma'am,
how it can be checked.
ma'am, there is no halt bit in my overflow
Yes,
bit.
ma'am.
I will
Yes,
show you.
ma'am. Same
Okay,
here.
okay, I will show you.
Yes, ma'am. In mine also.
Okay, no problem. No problem. I will show you how to set the hold bit. Okay. In fact, you will see a micro instruction here in this list today. Okay. But I will show you. Now, so in the first lab sessions of this week, that is yesterday, it was for B1, today it is for B2, and Friday it is for B3. You will be completing fetch sequence and CLA. Okay. In this second lab session, so B1 and B2 have their lab sessions on Thursday. You will be doing what? You will be implementing the rest of the instructions, rest of these instructions. Okay, so I request you to please look at the execution of these. Now I will be explaining to you. So look at this explanation very carefully. And B3 will be doing the same thing on Saturday. Okay, the execution of these. Okay, so let us first complete this. Okay, so CLE means the E bit. What is the E bit? E bit stands for,
Extended bit.
it is for, I'm sorry, come again. Extended bit, yes. So E bit stands for the extended bit, right? It is the leftmost bit. It is an extra bit. It is an extra flip-flop that we assume is attached to accumulator, if you remember. right? It is generally used to store the overflow, and as you will see in some operations such as circular right and circular left, we again make use of this E bit. Okay, so CLE means simply clear the E bit to 0. Next is complement AC. Okay, so what do we have to do? We simply complement the contents which are there in AC. Okay, similarly CME. So CME means complement the E bit. Okay, now I'll take these two instructions in a moment. Let me first complete the other instructions. The next is increment. Okay, so increment simply increments the contents of AC by 1. Okay, whatever are the contents of AC, suppose they are 0 earlier, then they will become 1. If the value of AC is 1, then it will become 2, and so on and so forth. Okay, then SPA. SPA stands for skip if positive AC. Okay, so if you remember, I told you that the leftmost bit in any register is reserved for the sign bit, right? Now, if the value of this bit, that is we know that the length of AC is 16 bits. So the most significant bit or the leftmost bit is the 15th bit. If this bit is 0, that means AC is positive. And what are we saying? Skip if positive AC. So what is to be skipped? The next instruction which is written in line to be performed is to be skipped. Okay, so what are we telling the processor? We are saying that please don't execute the next instruction if the value of AC is positive. How to know whether the value of AC is positive? From the 15th bit. If it is 0, the value of AC is positive. Okay, now how to actually skip the next instruction? That means how to not execute the next instruction. That means how to jump to the next instruction. Okay, how to do that? Now we know that PC holds the address of the next instruction to be executed. So if I simply increment the value of PC by 1, what will happen? It will now start pointing to the next instruction instead of the next instruction. Okay, and we don't need to make any other change. Now when we go back to we have done our job, we were here. Okay, to execute SPA we were here. We have done what? We have incremented the value of PC by 1, and after that we go out here and we start executing the next instruction cycle. Now when we start executing the next instruction cycle, please say the PC has the address of the next instruction automatically. Okay, so as a result, which instruction will be fetched? Next instruction. Okay, and that instruction will later also be executed. So automatically the next instruction is skipped. Is this clear? Right?
Yes.
Yes, ma'am.
Okay,
Yes,
good.
ma'am.
Good. Next is skip if negative AC. So this is a simple instruction. If you've understood SPA, there is a little change here, and that is that we only need to check if this time that the value of the 15th bit in AC is 1. Okay, so if it is 1, then skip the next instruction by incrementing the PC. Right. Now next is skip if 0 AC. So this time we check if the value of AC is 0, then we shift PC to, then we increment PC to 1. That means we skip the next instruction. Next is skip if 0 extended bit. If the extended bit is 0, then skip PC. Then increment PC, that is skip the instruction. And the next instruction, please see the last in this line is halt. Okay, halt is, now please see, there is a start flip-flop. Okay, there we assume that there is a flip-flop called start flip-flop, and we denote it by S. We denote it by S. So when we need to halt the execution of the program, okay, then what do? We skip the, we set the halt bit. Okay, what do we mean by this is that actually internally we are setting this S flip-flop to 0. Is this clear? Right? So now let us come to circular left and circular right. Okay. Now before I go on to these two instructions, let me show you two other instructions which are not listed here. Okay. These are also called the shift micro instructions. Okay. And they are generally denoted by shift right and shift left. Okay. Now what is shift right, shift left? When I say shift right, then each bit, suppose this is the original value of accumulator. This is the original value of AC. Okay. Then when I say shift right, what will happen is each bit shifts one bit to right. So this bit, please see, gets lost. Okay, this bit occupies this position, this occupies this position, this occupies. So every bit keeps on shifting, and resultantly we have this position empty, which is then filled by 0, which is then filled by 0.
Excuse me, ma'am.
Yes,
Ma'am, are you teaching from the presentation?
yes. Why?
Are you on
Ma'am,
the execution of register reference instructions page?
No.
Now the page changed to shift micro instructions. It wasn't like this before.
Oh, there must be some lag in the network, I think. Okay, now what slide are you able to see?
Shift micro
You
instructions.
are able to see. So, okay, no problem. I'll just explain this again. Yeah, just give me a minute, okay? Yeah. Okay, so please see, let these be the original contents of the accumulator. Okay. Now, when I say shift right, then what will happen? Each of these bits shifts one position to right. So when this bit shifts to right, it has nowhere to go. All these bits shift right one by one, one by one. So when this bit shifts, it has nowhere to go and it drops down and it is actually lost. This bit is lost. Okay. And we have this position empty now, okay, which is filled by 0, which is now filled by 0. Any problem in shift right? So the basic thing is that every bit shifts one position to right. Any problem?
No, ma'am.
Okay. Let us look at shift left next. Now, what happens when we shift left? Similarly, all these bits are shifted one bit to the left. Okay, and this time the most significant bit drops down and is lost. Is this clear? Right? And this position now becomes empty, which is added with a 0. Any problem?
No, ma'am.
This is called as the normal shift. Now there is also a variation of this which is known as arithmetic shift. I'll just show you. Now please see, in the arithmetic shift micro instruction, what happens is we don't shift the leftmost bit. Okay, so this entire operation, it is depicted by ASHR and ASHL, that means arithmetic shift right, arithmetic shift left. Okay, but the only difference is that this time we treat this bit to be the sign bit, and therefore we don't touch it. Okay, the remaining shift operation is performed as it is, so this bit will remain as it is. Okay, and the remaining bits will be shifted right. Okay, similarly in arithmetic shift left also we will not be shifting the sign bit, and remaining bits will be shifted. Okay, we will I'll give you some examples of arithmetic shift in micro instructions, or maybe you can look at the back of your textbook to find an example or two to practice for the shift and arithmetic shift and circular shift micro instructions. So sometimes these questions come that if these are the original contents of AC, then what would be the contents of AC after we perform circular right or circular left, or arithmetic right or arithmetic left, or shift right or shift left. Okay, so you should ideally, just do these 2-3 simple calculations with your hand. Okay. Now let us see this circular shift micro instructions. So circular shift micro instructions, what happens is that no bit is lost. Okay, no bit is lost. This is like shift micro, the first shift micro instruction that we had seen. And the only difference is that this time when I say, now this time I'm saying circular shift right. Okay, so when I say circular shift right, then what happens is all these bits are shifted to these bits are shifted to one bit right. But when this bit is now shifted, it does not fall down, it is not lost. Okay, instead it is copied to E. Instead it is copied to E. Okay, and whatever is stored in E is passed on to AC. Okay, so it becomes a circle. It becomes a circle. So this bit that is falling from here, this bit that is falling from here is actually brought here to take place of E, and to make its place, the bit in E is shifted into the accumulator. Okay, so you can see this listed in the micro operations here. So this is a machine instruction. You can see that CIR is a machine instruction which consists of so many micro operations, that is micro instructions. Now each of these is a micro instruction in its own. So the first micro instruction is that AC is the first thing that is performed is that AC is shifted one bit right. Okay, and then the E bit is shifted into the 15th bit of AC to make place for the 0th bit of AC, which is after that this AC 0th bit is then shifted to E. Is this clear? So is this clear to you what is happening here now?
Yes, ma'am.
Any problem?
No, ma'am.
Okay. So that concept is also clear to you now, that one micro instruction, one machine instruction is equivalent to so many micro instructions, right? So there are so many micro operations which have been performed here. Now CIL is, the concept remains the same, that means nothing is lost now. Instead, there is a circular pattern in which these bits revolve now. So if this is the value of AC, then this one will be shifted to E. Okay, this one will be shifted to E, but to make place for it, the value which is there in E is first shifted to AC 0. Okay, so you can see that I apply normal shift left, this shift left, if you remember this shift left operation, shift left that I shown you here, okay, operation on the AC, okay, so that every bit starts going one bit to the left, and then E bit is made free by shifting it to the AC 0 this time. Okay, so we shift this to 0, and then this bit which was falling off from here is put inside the extended bit flip-flop E. Is this clear? So this is these are all the register reference instructions now. Okay, I hope you don't have a problem. You have understood all these. These are clear to you?
Yes, ma'am.
Right. So in the next class, then I will show you how to set the halt bit. I don't have CPU sim right now. So I will show you how to set the halt bit, and also maybe, show you the execution of one or two micro instructions out of these, so that you can perform the remaining yourself. Okay? Just give me a minute. I'll be sharing the attendance now. Please mark your attendance.